Hello, this is Professor Kuehn. We have been talking about Einstein's book, Relativity. The reference is A Student's Guide Through the Great Physics Texts, Volume 2, Chapter 29. In the last couple of lectures, we've been talking about both the principle of relativity and the principle of the constancy of the speed of light. Over the next several lectures, everything that we're going to talk about, all of these strange consequences that you might have heard about with the theory of relativity, will follow deductively from these two principles, the principle of relativity and the principle of the constancy of the speed of light. Now, I want to make a couple of comments about how Einstein's approach to space and time differ from the approach that we came across with Isaac Newton in his Principia, that is, Newton's approach to space and time. Now, remember that Newton, in his scholium back in, I think it was chapter 20, his scholium on absolute and relative motion, he claimed that we typically talk about motion as being relative and space as being relative, and time as being relative, but we still want to keep in mind the notion of absolute motion and absolute space and absolute time. He thought that there was absolute time. That is, there's a reference frame of time that moves the same for every single observer. And likewise, there is a reference frame of space that is the same for every single observer. That is, he thought that space and time, at least absolute space and time, were fixed and immutable. Now, how is Einstein different? Einstein, on the other hand, is going to claim that the speed of light is fixed and immutable. And as a result of this, space and time themselves become flexible ideas. So whereas Newton thought space and time were fixed and the speed of light must be relative, Einstein is going to flip this and say that the speed of light is absolute and hence space and time must become relative. So in a sense, both Newton and Einstein are relativists. They both believe something is relative or something depends on the observer. They just disagree about what that is. And likewise, they both are absolutists in the sense that they both believe that there is something absolute or observer independent. Newton thought it was space and time. Einstein thinks it is the speed of light. Okay, so what I want to do now is I want to outline a few of the important consequences of accepting Einstein's principle of relativity and his principle of the speed of light. So that's what I'm going to outline here in the next few minutes. So, what are the consequences of accepting, one, the principle of relativity? You might remember that the principle of relativity says that the laws of physics are the same for any inertial observer. And two, the constancy, or the principle of the constancy of the speed of light. That is, the speed of light is the same for all observers, regardless of their motion with respect to the source of the light. And I'm just going to outline these four consequences. So these are the assumptions of Einstein's theory of relativity. And what are the consequences? Okay, so the first consequence, I'm just going to name a few of these, and then over the next several lectures, I'll talk about these in more detail. First is that the order of events may be different to observers who are in motion relative to one another. So I'll just say this and I'll explain what I mean by this. So the order of events may be different to observers, or as measured by observers, to observers who are in motion relative to one another. Now, in order to understand this statement, we have to understand what we mean by an event. So there's a kind of colloquial way that people use events, like, I went to a concert, that was a really fun event. In physics, the idea of an event is something a little bit more precise. So by an event, we mean something that has specific space and time coordinates. So for example, if I snap my finger, that would be an event. What do I mean by that? It has a particular x, y, and z coordinate. You might say in my room here, in my library that I'm talking about, I might define the origin of a coordinate system in the corner of my room, and then the x-axis would be along the wall this way, and then the y-axis might be along the floor this way, and the z-axis might be up. So I'm snapping my fingers, and the x, y, and z coordinates might be 3 meters along the x-axis, 1 meter along the y-axis, and 1 meter along the z-axis. Those would be the x, y, and z coordinates of that event. But there's also a time coordinate, so it is happening at exactly 8:34 in the evening. So there are x, y, z, and t coordinates for this. That would be an event that we're talking about, okay? Another event might be someone slamming the door at 2 o'clock in the afternoon. That would be an event, okay? So, and the point is that in this first point that I'm making is that the order of events may be different to observers who are in motion relative to one another. So, for example, if I'm going to snap my two fingers, I might snap this finger first and then this one second. So I see this event happening before that event. Now it's possible that there's another observer who's in motion relative to me, who's moving at some high speed compared to me, who may see this event happening before this event. That is, the order of those two events may be different for observers who are in motion relative to one another. That is going to be one of the first consequences of accepting the principle of relativity and the constancy of the speed of light. What is another consequence of these two postulates? Well, moving clocks tick slowly. This is sometimes called time dilation. Okay, so what do I mean by that? Well, imagine that I have a wristwatch and it ticks once every second. So I'm looking at it, there's a tick one time every second. Now, if I am running past you at a high speed, let's say I'm going in this direction at some very high speed, and this is going to become more pronounced as my speed approaches the speed of light. Whether that's practical or not is another issue, but as my speed increases, if you're looking at my watch, you might see my watch ticking, instead of once every second, you might see it ticking more slowly. That is, maybe once every 2 seconds when you compare it to your watch, which is on your wrist. Okay, so moving clocks tick more slowly. That's the phenomenon of time dilation. What's the third consequence? Is that moving bodies or moving objects, moving bodies are shortened in the direction of motion. We'll talk more about that in a few minutes, but this is called length contraction or relativistic length contraction. So let's look at my pen for a moment. This pen, let's say, is about 8 centimeters long. It is at rest relative to me. It's an 8 centimeter long pen. If I were to hold up a ruler to it, it's about 8 centimeters. Now, the phenomenon of length contraction says that if I am running past you at a high speed, holding this pen, once again at a high speed, close to the speed of light, when you try to measure the length of this pen, you will see it shortened compared to me. You might say this pen is only 4 or 3 or 1 centimeter long. That is the phenomenon of length contraction, and that is going to be another consequence of accepting the principle of relativity and the constancy of speed of light. And then finally, what I'm going to point out is that moving bodies or moving objects, moving bodies are more massive. Moving bodies are more massive. Okay? In other words, the mass of an object is not the same as its rest mass. Okay? In other words, if you were to try, we can debate how you actually measure the mass of something. That's going to be a critical issue here. But if you were to somehow measure the mass of an object that is sitting still compared to you, you'll measure a certain mass of that object. But if you were to find a way to measure the mass of that object when it's moving at a very high velocity, it's going to behave as if it had a higher mass. Okay? So moving bodies are more massive. Now, these four things, you might be tempted to say these are just like moving clocks appear to tick more slowly, but they're not really ticking more slowly. Moving bodies appear shortened, but they're not really shortened. Moving bodies appear to be more massive, but they're not really more massive. That is an incorrect way to think about these things. Why is that? Because the idea is that any inertial observer, that is any observer who's moving at a constant velocity, is put it this way, there is no preferred inertial observer. So there's no way of saying which particular observer is correct about the speed of a clock, or correct about the length of an object, or correct about the mass. So if people measure different rates between ticking of a clock, measure different lengths of objects, measure different masses, there's no principled way of discerning which is the correct answer. Okay, so that's something we're going to be talking about in the next several lectures. Okay, so tell you what, I'm going to stop there, and next time I'll talk a little bit more about the first point, how the order of events may be different to observers who are in motion relative to one another.